All right, everybody. Today it's time for another Crack Me, and I picked out this one called Flags, and it's written in pure assembler. So we're going to do some pure assembler reverse engineering. We're not going to decompile this using some tool. We're going to look at this file line by line until we find the password. All right, and this is a pure assembler binary. No tools, just pure fun reverse engineering this. So let's jump right in. I've already downloaded the file. It's right here. And let's have a look at what it does. It does the following. It is prompting us, you like flags, I like flags, can I have a 01 please? And when we enter any password, for example, this one, then it says that I don't think that's the flag I was looking for. If we enter a different password, then it still says, I don't think that's the flag I was looking for. So what do? We first, before we do anything else, we check the binary, whether it contains any strings that look suspicious. And calling the strings utility, it just tells us that there are the strings that we already have seen, the prompt, then there's a thank you note. Thanks, that's perfect. That is probably the message that we see when we enter the correct password. And then there's the failure method or message, and then that's it. Those are just names of sections in the assembler. Or rather in the assembly, in the compiled binary. All right, so what do? Let's do an object dump, and let's dump all sections to the console and pipe that into less. And as you can see, there's a text section that is reasonably big. Well, no, we can handle that one. It's not big. It's a normal text section here. The text section is what contains the code, and that's why we can't read anything here. So this consists of opcode and register names and values that are moved back and forth. We can't really read it right now. And then there's the data section. The data section contains strings, the strings that we have already seen. And it looks like that's it. Actually, the data section completely consists of strings here. And it looks like this last part is not a string. But also looking at the hexadecimal values here of that last part, it looks like this is just zeros. 0A, 00, 00, 0, 0, 0, 0A. So I'm not sure if that is any password embedded here, not even an obfuscated one. That would be unusual. All right, so instead of looking at a section dump, a hex dump of the sections, let's look at the disassembly in Intel format, because that's a nicer assembly format and that's how it looks like. And just to show you the difference, the AT&T syntax looks like this. You have all these dollar signs and percentage signs. And then this syntax here, it's hard to read. And this effectively means, let's remember this OR statement here, or maybe that's the first one that I can use to explain. Let's have a look at this OR statement here. This means take the value from the rax register and OR it with the BL register and then put the result into the BL register. I find this very hard to read. This is awful. And the same thing for any adds or subtraction. Same thing. I don't know if there are any here. But the Intel syntax is nicer to read. Let's have a look at that. So where's that same OR statement here? there it is. So this is the OR. We have the BL register, and then there's a, then this tells us there's a byte pointer, rex, and it is ORed with BL, and the result is put into BL. I find this a bit more pleasant to read. Also, it's not all cluttered with these percentage and dollar signs. All right. So, as I promised you, we're going to do this without any special tools, no decompilers, no reverse engineering software like IDA or Ghidra. So my approach to reversing this would be to create an object dump of this, and instead of piping it into less and just jumping here and trying to reverse engineer anything here and keep everything in our head, let's just create a file and call that file the assembler, or maybe code.assembler, and let's open that file in Vim and see whether we can read it. Now I also need to disable my linter, and then that's it. I don't know if the syntax highlighting is correct. I think the light blue one, the light blue stuff is, I'm not sure. The light blue stuff might be the opcodes. No. I have no idea if the syntax highlighting here is correct. Vim is attempting to do some syntax highlighting. It seems to highlight all the constant differently from the registers themselves, but I don't know if that makes sense or that syntax highlighting here makes sense. I'm not sure. I don't think so. We could also do syntax off to disable it. Is that easier to read? I don't know. Let's keep it on. And let me know in the comments how I can fix up my assembly syntax in Vim, if any one of you knows. All right. So the text section is what is the stuff that is the actual code, and what's happening here is, let's start with the first line. We have a register RDI, and the value 402000 is written into it. And it's very likely that this is a pointer, because the addresses to the left here look very, very similar. So if we search for 402000, then the result is not found in here, but it might be found in the data segment. So let's have a look at that here in this other terminal. And we can then switch back and forth between the segments and the disassembly. Object dump. And yes, indeed, as you can see, that right here is the data section, and this is the address that the disassembly is pointing at. So the RDI register is pointing at the start of this message here. So very likely the message is going to be loaded in this call method, I would assume. So this is a call, and the call also takes a constant argument here. So let's have a look what that is. And we can even put a comment here or above. Let's put a comment, or let's put it below or above. No, let's put it above. I think comments are always started with a semicolon in assembler, as far as I know. Assembler comment. Let's look up assembler comment, assembly comment. Yeah, in assembly, comments are usually denoted by a semicolon, although GAS uses percentage for single line comments and this for block comments. All right, I'll use the semicolon. I have no idea if I'm even adhering to proper assembly syntax here. So let's write down here, loads the input prompt, the input prompt message pointer into the RDI register. And just like this, we're just going to disassemble everything line by line, or maybe not line by line, but everything where we can get some reasonable information out of the assembler code. We can just write a comment like this. And so we don't have to remember everything in our heads. So let's have a look at what that call right here does. Because call is a function call, and let's see what that function call points at. It points four oh one 140. 401 140. That's the location that it points at. And this seems to be a function entry point, so let's just annotate it like this, because there were multiple calls to this function. Let's just write function entry point here. And also, whenever this function is called, the RDI register is set before it, also up here. So we can also write that very likely this function uses RDI. RDI is argument. Just like this. I mean, the fact that RDI is set before this function is called is a strong indicator that RDI is a function call. That this function here is a, well, what? The fact that RDI is set is a strong indicator that this function is using RDI. It's not proof, but it's very, very likely. So let's find out. First of all, this function sets or XORs RCX with RCX. What does this mean? This means that right here, RCX is 0 or is set to 0, because this is roughly equivalent, I think, to move RCX and 0. And then let's save that. And as you can see, it's set to 0 and immediately incremented. RCX is incremented here. And then there's, well, what's the next thing that's happening here? So, okay, now the input argument RDI is used, RDI. And RCX is multiplied with 1 and added on top of RDI. And this looks like this is an array access. Why does it look like an array access? Because RDI is a pointer. It has been loaded with an address before. It has been loaded with this address before. And then RCX starts with 0, is incremented. So this is now 1. And this looks like it moves the location of the first, not the 0th character, into DL, into the DL register. And then there's a check that checks if DL is 0. No, that is a meaningless check, I think. No, if DL and DL are, well, that's basically an AND operation. And if the result is, yeah, that's an AND operation that doesn't set the result into any, that doesn't write the result into any register. Now, what's happening here is that the 0 flag is set if DL is 0, else it's not set, and the 0 flag is a special register that is set on test or compare instructions. Probably there are more instructions than that, but that's just another register that is set in the background. And if the 0 set, and then there's a jump if not equal, and that jump goes, where does it go? It goes up here again into this line 401, 143 and increments RCX again. And then another character from the pointer is checked. Byte pointer moved into DL. So this basically looks like the individual well, does this mean that it accesses the values stored in RDI plus a specific location? Or does it? I'm not sure. Byte pointer. RDI plus RCX multiplied with 1 is written into RDX. I think we should look this up. Assembly Intel byte pointer. Okay, it seems that the byte pointer tells you how large of a value to grab from that memory location. So in this case, a single byte, that means a single byte is taken from this memory location and then tested here, that the value is taken from the memory location, written into DL. DL is checked if it is null, a null byte. So that means all bits are set to 0. And if all bits are set to 0, then the test will fail. And no, if the bytes are not 0, then the jump, if not equal, will jump back up here. 401, 143 is here. And then this will increment the RCX again. Then it will check the next character. Is it null or 0? Is it completely zeroed out? No, not yet. Then it jumps back up here, increments, reads the next character, checks it, and let's say the character is null or 0 now. And then this jump, if not equal, is not triggered, and then it moves the RCX into RAX, and RCX is the incremented counter. So what does this mean? This means something is incremented until a 0 byte is encountered, which means that this is a string length counter. So having a look at the memory here, you can see that this is the string that is being parsed, or not parsed, but it's being scanned, and it's being scanned until the first 0 byte is encountered. And where's the first 0 byte? Let's see. And there it is. Which makes sense because this string ends right here, which corresponds to this location. And a 0 byte is always in hexadecimal 2 zeros. Yeah, 1 0 is just 4 bits, and a byte is 8 bits, so we need to have 2 zeros here. All right, so this counts the length of this full string, or this function here is a string counter function. Counts string length of input string pointer RDI. And And that's how we reverse engineer the first method in this code. All right, so let's go back up and see how we can continue. So back up at the entry point of the method, let's see what else we can find out here. The next thing, well, what's now happening is that the string length is checked for this string. And we can summarize this in a comment here. Check string length of string at 0x402000. Yes, strictly speaking, this is the string pointed at by 40200. But I think everybody gets the point here. And then the same string is loaded again and moved from... Ah no, not moved from. The RAX still contains the string length because it was filled in this call right here. So RAX actually contains the length of the string and it's written into RSI. And then this call right here is made. And now we can also already have a clever guess. We load the string again, plus the string length, and then because that's the prompt that is printed out to the user right at the beginning of the invocation of the executable, that's probably going to be a printout command. So let's jump right there. And as you can see, there are a couple of such printout commands. Let's just check the disassembly here and already write a comment. Oops. Prints out string at RDI of length RSI, I think. Let's save that and let's just try to confirm it. So we have the length at RSI, it's written into RDX. The RDI is the string and it's moved into RSI. Okay, so data shifted from RSI to RDX and then from RDI back into RSI. But this looks like the preparation of arguments for the system calls, which we have learned about in the last episode. And this is the system call denoted by EAX value 1. And this is, if you remember it from the last episode, this is system call. This is system call write to file pointer. Let's have a look. And yes, as you can see, system call 1, if RAX is 1, which is the same as EAX. EAX is just the 32-bit subspace of RAX. RAX is 64 bits. It's the full 64 bits variable or register, and EAX is the lower 32 bits of RAX. And that's basically the case for all registers that start with R and with E. R is always 64 bits. E is always the same location, but it's the lower 32 bits. So this one has the value 1 and it's therefore causing a syscall called system write. And EDI is probably going to define or is defining, yes, the file descriptor at which we want to which we want to write. So we specify the file descriptor that we want to output to. In our case, it's 1 because 1 is standard out, but we could also write to a file. Then RSI is the pointer to the string, which is why RSI is filled with RDI, which is the input argument. So the input argument is RDI. And because the syscall needs that value in RSI, it's moved into RSI here. And RDX rdx, where is it? rdx is the count, the string length. And yes, that's why the length RSI, which is the input to this assembly method, is moved for the system call into rdx. All right. And then there's the system call and a return statement. So this is effectively the print out function. And let's put here end print function. End print to standard out function. All right. That's the next method that's being called, and let's annotate that here as well. Prints string to standard out. Prints, and what string does it print to standard out? It prints out the prompt message to standard out, and now we can guess already what the next statement is, because there's another syscall here, and my best guess is now that this next thing is going to be the input, the user input. So let's check. So we set EAX and EDI back to 0. EAX 0 looks already suspiciously like the system read call here. So this is the system read call. Remember that RAX and EAX are in this case the same, because E is the lower 32 bits of RAX. Now the EDI command, or the EDI register, denotes the file descriptor again. So file descriptor 0 in our case is standard in. So that's what the user inputs. And then RSI is that's the buffer into which the string is being read. So the user types something, hits enter, and then that string is read from standard in into the buffer that's specified via RSI for a count of RDX. Okay. And RDX is 0x8. So here there's an input into this location for 02090. And that is a location beyond the executable. As you can see, the last address here is 402080. And of course, if the user enters something, then it's going to be written into memory beyond the program's runtime memory. It's going to be written on the heap or stack. I don't know what exactly that here is, but this is written into some memory reserved to the application. And then EDX is 0x8, and that should mean that the string, the input string that is expected, has a length of 8. Then there's a syscall, and the syscall now reads from the user. So we can input a string of length 8, and it's written into this location here. So let's annotate this syscall here. Reads string of max length 8 from standard in. And now what happens next? There's a push F function. And what happens here? Actually, how much more is there? Oh, there's quite a bit. Down here's our next annotation. It's the function call. And then we're up here. So this moves the value 7 into EAX, the value... Right. So this sets EAX to 7. Then RAX, which is the same as EAX, if you remember correctly, is subtracted by A, which is a hexadecimal 10. It's a decimal 10. So RAX, which is 7, is subtracted by 10. So RAX should contain the value minus 3. And then EBX gets the value 3. And then there's an add statement adding RBX, which is 3, because this is the same as EBX, onto RAX, and RAX is minus 3. So we have minus 3 plus 3 is 0. So all of this stuff here, all of the calculations above, simply set RAX to 0. This is just for confusion. And then there's a push F. What is push F? Let's have a look. Push F. Push F, push eFlags register onto the stack. As you all know, in assembly there's the eFlags register. Usually you don't use it, but push F pushes the value of the eFlags register onto the stack. This means it's pushed onto the stack. The flags register is pushed onto the stack here. Let's annotate this. Flags register is pushed onto the stack. And then pop. What does pop do? Pop takes the last value from the stack and puts it into this register. This means flags, which is the last value on the stack, push F pushes something onto the stack, and pop removes it from the stack and writes it into this register. This means that flags are written into R10, into the R10 register. And then, whatever the point is, because there's this AND statement here, there's an AND statement here, and the AND statement wipes out the lower 4 bits, zeros, the lower 4 bits. So if we take R10, or R10, and perform an AND operation with hexadecimal 0xF0, then this will result in the lower 4 bits zeroed out, because this is 1111 0000. Okay. Oops. Let's just take this for granted and not question it right now, whatever the point of that is. So here we just zero the lower 4 bits. And we keep the other ones. What are the other ones? Is there any documentation on the bits of the flags register? Flags register 86. I don't know, probably I have to look up the eFlags register, but I'm not sure. It's documented down here. So we are dealing with the flags register, and the traditional flags with an S. Flags register contains of 16 bits, starting with 0, ending with bit 15, of course. it has some bits that are now zeroed out. The first 4 are zeroed out, which are the carry flag, something that's always 1, a parity flag, and then something else reserved. So this looks like it's meaningless, and the flags above that are left intact. The next 4 are left intact, which are an auxiliary carry flag, whatever that is, a 0 flag, that's the important one that we frequently use when jumping statements. With jumping statements, jump if equal, jump if not equal, jump if 0, and because the test and compare conditions set that 0 flag. So this is something you will encounter more often. And then there's the sign flag, which is also apparently it's set sometimes. I don't know when exactly. Maybe if a calculation has a negative result, then it's set or something like that. And the flags above that, they are also zeroed out because implicitly this is an AND instruction with 0x000000, etc. f0. So the only intact bits, the only set bits are the bits 3 to 7, I think, or 4 to 7. Okay, whatever the point is of that, no idea. Then there's a load effective address statement here, and it loads an address 0x402090 into racks. What is this address? 402090. Do you remember this address? Did you pay attention? Let's scroll up a bit. It's coming from this address right here, which reads a string from standard in into this location. So this right here is an address. This right here is an address that the user input is written into. So RAX will point to the user input, and the DS, let me just look that up, assembly DS address. In assembly, DS is the data segment register. No, is it that? No, it's not. DS syntax. Meaning of DS: in assembly language. The 3E byte in the first instruction is a DS segment override prefix. In this case, it's redundant because DS is the default segment for most memory accesses. Also, if you have a 32-bit memory space, you typically never explicitly specify the segment registers since they are set up to point to the same memory anyway. Well, DS stands for data segment, and that's basically the segment that the user writes into. That's my understanding of it. All right, so this says from the data segment, get this address. This address is only available in the data segment, so probably this is superfluous, but this just makes us explicit probably that we are accessing an address outside of the executable during runtime. At least that's how I explained it to myself. I might be wrong. Correct me in the comments if I'm wrong. And now this address is written into RAX, so RAX will now point at the user input. Let's write that here. RAX point RAX at user input, and then write value 5 into ECX. ECX is, by the way, commonly used as a counter. That's why it's called ECX. Originally, this was just CX. Then for bigger machines, it was called ECX for 32-bit machines. And for 64-bit machines, this is This can also be referred to as RCX. All right. And then there's an XOR, which basically wipes out the value of RDI. So here our RDI is set to 0. Yeah. An XOR always sets a bit to 1 if only one of the two input bits are exclusively 1. Because we're specifying the same bits twice, or the same bit sequences twice, all the bits always have the same value. That means no bit is exclusively ever anything, and that's why RDI is set to 0 here. So XOR something with itself is always 0. Then there's a compare statement that compares RCX with the value 0. So here's the check. Is RCX 0? Maybe is RCX 0? If it's 0, jump if equal. Jump if equal only jumps if the 0 flag is true. That means, and that is only the case if RCX is 0, okay, and then let's see what happens here. This zeroes out RBX. RBX is set to 0. And then the byte pointer, which we learned earlier is the lowest byte dereferenced from this pointer, which means the first character from the input, because RAX points at user input. Right here, this is our comment. So RBX is set to 0. RAX is this byte pointer is the first character written into RAX or pointed to by RAX. And that character is ORed with BL. What is BL? What's the value of BL? BL is the lowest 8 bits. It's the lowest 8 bits of the RBX register. RBX is 64 bits. And BL is the lowest 8 bits of that register. So here the lowest 8 bits are ORed with this character. And this is just a way to write those bits into BL, because here BL is zeroed because RBX is zeroed, and RBX is the 64-bit register that is the parent register, let's call it that, of BL. Yeah, so if RBX is set to 0, that means that BL is also set to 0 because it's the lowest 8 bits. And then we write the first character of the user input into BL. And this OR operation writes the bits into BL because BL is 0. And therefore, all the 0 bits, and because all the bits are 0, any bit that is 1 in this byte right here will be a true result in an OR operation. So 0 or 1 is always 1. And 0 or 0, in case this byte contains zeros is always 0. So whatever is written here, whatever the bit values are here, they are copied over into BL. Now, next, or maybe we should annotate this. Copy first character into BL. First character user input. And the next instruction is a SHL instruction. That's a shift left. What does a shift left do? Well, I hope you can read this all well. If I make it like this, I think it's less readable. Let me just try to reopen it. AL disable. Is this easier to read? I don't know. I think this is nicer. Just have to pay attention that my webcam is not overlapping the screen. All right, so let's keep the instructions at the bottom here. So this is a shift left, and this is the character that the user entered, the first character that the user entered, and it's shifted left by CL. What is CL? CL is the same thing as BL, or conceptually the same thing as BL. CL is the lowest 8 bits of the RCX register. And RCX is... what is the value of RCX? It's 5, because RCX... but because 5 was written into ECX, which is the lowest 32 bits of RCX. Yeah. Then there's the check whether the value of RCX is 0. It's not, because it's 5. Let's write that here. And then there's this shift left operation, which compares BL with... which shifts BL by CL, and CL has the value 5 right now, because it's the lowest 8 bits of ECX or RCX, depending on how you want to put it. So this is a shift left by 5 bytes. So let's have a look at the next operation. Then there's an AND operation between R10B and BL. What is R10B? R10B, it looks like this is the lowest byte, the lowest 8 bits from R10. And R10 is the flags register from which some bits were zeroed out and some were left intact, among which was the 0 flag right here. So these couple of flags were left intact, these ones. And this performs an AND of this flags register, because the flags are popped into R10 here. Remember, there's the push F from the flags register into R10. So flags are pushed onto the stack and then popped off the stack and written into R10. Then R10 is just cleaned up a bit. And then the next time R10 is referenced is down here, and there's a check, or there's an AND. There's this AND statement that says R10B, the lowest 8 bits of R10, and BL, R10B and BL, and the result is stored in R10B. Okay, that means we perform an AND between flags and character and input character. Perform, let's say, flags equals, or not flags equals, but effectively it means flags equals, no, that's wrong. Flags and input character. Let's leave it like this. And then the result is written onto the stack. No, push. Yeah, push writes a value onto the stack. And then writes value, writes result onto stack. Then RAX is incremented. Remember, RAX is the register that points at the user input, which means that this now points at the next character. And RCX, which is the counter, which is starting at value 5 up here. RCX is a counter, C. ECX is also the counter, it's just the lower 32 bits. This is the entire 64 bits register. The entire 64 bits register is decremented. So here, counter is decremented to 4. Then there's a popf. Popf. What does popf do? It's basically the reverse operation of pushf. Pushf pushes the flags register, the value of the flags register, onto the stack. And popf pops off the last value from the stack and writes it into the flag register. We can just also confirm this. Popf assembly. And as you can see here, pops the word or long from the top of the stack and stores the value in the flags register. Stores a word in flags, so that's 32 bits, or stores a long in eFlags, 64 bits. All right. So popf is, well, that means that the last value from the stack, which is this here, it is the result from this AND operation. This is written this is written into the flags register. And then there's a jump. And as you all know, jumps happen only if a certain bit in the flags register is set. Which bit is it? It's the 0 flag. So if the 6th bit in the flag register is set, then this jump happens. Jumps if 0 flag is 1, which was just set through R10. Well, it is only set through R10, of course, if BL, the character, and R10 result in this flag being set. And if the 0 flag is not 1, then what happens? So there's another jump command here, unconditional, that jumps to 401.089. And this is down here. So this jumps here. And there's another address moved into RDI, which looks suspicious because RDI was previously used for printing out stuff to the console, for pointing at stuff. and this is the address 402.056. So let's check out here what that is. 402.056, it's right here. And this is the message. I don't think that's the flag I was looking for. So this is the error message that is being printed here by the print method, which we have found out at the beginning of this episode. So here, this is the error message, and this prints the error message. And then below this, wow, there's still a lot here. Well, okay, let's have a look at what that jump does here. So if this 0 flag is 1, then it jumps to location 401.067, 401.067, and that is up here again, which means the loop starts here again, and there's the counter, and it's checked whether that counter is 0. If it's 0, then this condition will be triggered and something will jump somewhere. Else, if it's not 0, then this value is effectively now 4, not 5 anymore, because it was decremented down here. This means that we continue here, retrieve the next character from the user input, perform a shift left by not 5 bytes now, but by 5, then 4. In the next loop, 3, 2, 1, 0, I think, or maybe just 1. And then there's again this AND operation right here. So there's always the shift left, then the AND, and then there's the comparison down here. Was the 0 flag set? And now if you watch this carefully, you probably have a feeling that this is a loop starting with value 5, decrementing, and first we shift left by 5, then 4, then 3, then 2, then 1, then 0, and it depends on the user input whether the 0 flag is set or not. And if it's not set at any time, then this loop exits and an error message is printed. So the success will happen if the user input is created in a way such that the 0 flag is always set by shifting left those bytes here. So let's have a look at what happens if the counter up here, the counter register, if it's decremented down to 0, then it's compared here. What happens then? Then there's this jump to 400.084, and this is right here. And I expect that, this pushes R10. This pushes R10 yet another time onto the stack and writes into the flags. And then there's this jump to 401.0b6. I don't want to know how many times I said today 400, but it's 401. 401.0b6. And 401.0b6 is down here, which is just one line after the printing of the error message, which is this. This up here is the printing of the error message. I don't know what this right here does. It's also something from, I don't know. We will see, I think. So this jumps to 4. No, this moves something into RDI. What does it move into RDI? It moves into RDI 40203D, and 40203D is something that starts at the end of this memory location here. And it says, thanks, that's perfect. So that's the success string written into this register or pointed to by this register. And then this printout method is called again. Success string, and prints success string to stand that out. And then there's, no, this is probably, sorry guys. This is probably the string counter method, and this right here writes the success string into the same register again and prints the success string down here, because this was the counter variable that was set. Success string. This was the string length method. So let's comment that, string length. And the same up here as well. So this doesn't print the error message. This is string length of the error message. Hope you can see it. So like this, now you can see it. This is the string length for the error message, and then the error message is written into RDI, and then right here it is print to console of the error message. And then move EAX 0x3c. Let's have a look at the syscall table, because that's again register preparation for a syscall. And this is the section that was where I said, oh, we didn't jump into this. What is that about? That's just another syscall after the error message. So let's check that out. Syscall and syscall. Where's the syscall table that we had opened earlier? Here. And then 03C is the value that is written into EAX. Syscall table. Let's look up a syscall table that contains also hexadecimal values. Is there one? I saw one at one point. No. Okay, then let's look up 0x3c 2 decimal. And that's 60. So we can check out the syscall table over here and check out what syscall 60 is. And it's system exit, and the first argument is an error code, and the first argument is RDI. That means this is the exit syscall, error code 0, and it's invoked here. So syscall, or this is just calls an exit with error code 0, and the application terminates after this. Nothing happens after this. That's it. So that's basically what happens when you enter a wrong password. And if you enter a correct password, then there's at some point a jump down here to the success string, which is printed to the console. And then again, there's the 0x3c here with the error code 0 and the syscall. Let's annotate that with exit. Exit after success. And I think that's the disassembly for every single instruction here. We checked them all. No, we didn't check them all. There's some stuff down here. There are some syscalls down here. I don't know if we checked them. And to start, let's check if there's a jump to this part of the code. 401, 103. Let's search for that. 401, 103. No, there's no jump here. But this would be printing out something to the console from printing something to the console, standard out. This is the print to console EAX value. And RDX and RSI are probably initialized from the user input somehow. No, from the data somehow. And this looks like a regular printout. I just don't know whether it's used at all. This looks unused. There's no jump to this memory location here. And the lines before that say end print to standard out function. So there's the return here. So this will never go here. And also there's no jump here into this line. So this looks unused to me. I might be wrong, but this looks really unused to me. All right. Alrighty. What about this? This moves something from memory into RSI 40208C. 40208C. And that is this stuff back here, which is just meaningless. And then there's a syscall. Yeah, it looks like those are unused syscalls that are able to print something out, but they are never called anywhere. Because if I check out this memory location right here, 401.115, 401.115, then it's not referenced anywhere. So this might be there just for confusion. I don't know, honestly. So let's annotate those. Unused printout function. And this prints magic output, magic unused output. And then there's also a return here, and I have no idea what these instructions down here are there for, because this is some instruction and then a NOP, which is a no operation instruction. So this looks like this is also doing nothing to me. Whenever I see NOP, I just assume the entire line is doing nothing. I might be wrong about this. Please tell me in the comments if there's ever an instruction where a NOP is used, and the instruction and the instruction also does something. I don't know. And then here there's another NOP, so the argument here doesn't matter. This is just clutter. And just like this, I would say we have annotated the entire disassembly of our binary, and the core of what we need to solve now is just this shifting magic here. Right, where's the shift? Shift left, here it is. So we shift left the input first by 5 bytes, no, not by 5 bytes, by 5, 4, 3, 2, 1 decimal. And then we push the result eventually into the flags register here. Writes result into flags. And then this jump happens if the 0 flag is 1. So we have to construct the user input in a way that the first character, if it is shifted 5 times, must set the 0 flag to 1. The second character, if it is shifted 4 times, must set the 0 flag to 1. For the third character, must be shifted left 3 times, and the 0 flag must be 1. And the fourth character must be shifted 2 times, and the fifth character must be shifted once, and every time the 0 flag must be 1. What does this effectively mean? We take bytes or bit sequences of data and we shift them, and we have to hope that every time the 0 flag is 1. Now, I would suggest that we open a new terminal. Let's go into the correct me and let's solve this. And let's say the user inputs, and maybe I need just another terminal as well. Let's say, let's use this one. Let's say the user inputs the letter 1 as the first letter. Right here. This is the documentation. This is the ASCII documentation for the individual ASCII characters. So this column right here, this rightmost column is are the ASCII characters, and then this is the hexadecimal representation of them. So for user input 1, that has the hexadecimal value 31. So let's say the user enters 1. And by the way, we also know that the user is supposed to enter 5 characters because we loop 5 times over the user input. All right. I don't know if we just enter more characters, maybe they are just ignored. But we know that 5 characters are required. So let's say the user enters 11111 as input. And then we know the first character is 1, and that is a hexadecimal 0x32. No, it's a 0x31. And this means that this is a binary 0011 0001. Okay? And we know that the first character is shifted left 5 times, shift left 5x. This results in 0011 0001 shifted left 5 times is equal to, and by the way, I think, wait, there was also this stuff in the code right here where we zero out the lower 4 bits of the R10, which are the flags written on into which are the flags. And then R10, where is it used again? It's used somewhere down here. Right. Wait, what is happening? So we have the flags here. Then we zero out the lower 4 bits. And then we shift the character left, and then we perform an AND operation between the flags and the input character. That means whatever the input character is, the lower 4 bits are ignored. Can it? No. Oh, that is the lower 4 bits are. Oh no, I think this doesn't matter. So here we zero out the lower 4 bits, but they are meaningless down here because we want to only check that the 0 flag is set to 1. So it doesn't matter for this AND operation. What matters is the value of BL. No, wait, but something must be 1, otherwise this AND operation won't set something to 1. R10B contains the lower, no, contains the flags. R10 contains the flags R10B is the same as R10, but it's just the lower 8 bits. There's an AND operation with BL. And and if in R10B the 0 flag is set and it is set in BL, then it will remain set in R10. And that's what effectively ends up here in popf, because here R10 is pushed onto the stack, and then here the value from the stack is popped into the flex register, and that's used in the jump. And the jump is required for the loop to continue and for a success to happen. So we need to create the input in a way such that after 5 shifts left, the 0 flag, which is the 6th bit, this one right here, is set. So let's check. We are shifting this character 1 left by 5 positions. So let's see. Let's just write a couple of zeros here. So this one up here will go left 1, 2, 3, 4, 5. And those two will be shifted out of the register. This means that, is the 0 flag now set? This is the 0th bit, the 1st, 2nd, 3rd, 4th, 5th, but this is the 6th bit. So it is not going to work. So the 0 flag is not set here. Won't work. This means we have to pick hex ASCII characters such that the 0 flag ZF is such that the 0 flag ZF is 1. Okay. This means that we have to pick ASCII characters such that the 0 flag is 1. So, what does this mean? Let's just set the 0 flag to 1. This would look like this. 0, 1, 0, 0, 0, 0, 0. For example, this is a byte with 0 flag 1. And now let's shift that right 5 times. Shift right. And see what happens. What character we can get from that. So let's move the 1, 2, 3, 4, 5 positions to the right. This would be 1 to the right, 2 to the right, 3, 4. Maybe this one. This would be 5 right shifts. This is the 0 flag shifted to the right 5 times. Now we need a hex character that has this bit set to 1. So let's translate that to hexadecimal. For example, this first is a 0. These 4 bits are 0, so we write a 0 here, and these 4 bits are a 2. So this means that this 0 flag would be set by any hex character that has a 2 here. So we can pick 32, for example, but we could also pick 42 or 42, 52, 62, etc. But we could also pick any other character. We could also pick something that would be a 3, for example. We could pick 0, 0, 1, 1 or 0 1 1 1 or 1 1 1 1. We could even fill the entire bits with ones and have it working probably. But let's try it in a minimal way. Let's pick one where the last 4 bits resemble a 2, and that would be the 2, the character 2. Now let's do the same for the 0 flag shifted right 4 times. That would be this. This would be something that ends in a hexadecimal 4. And that would be a character 4. ASCII character 4 is hexadecimal 34, which has these bits set. Maybe I should put that in quotes to emphasize that this is the ASCII character that we are referring to. Then let's shift it right 3 times. And that would be an 8. So we have to look up the 8 here, and it's hex code 38. Eight is, for example, this. I should also write here, for example, 0x38. And now comes the interesting part, because now we have to still shift the register, but only 2 times. That means the rightmost bits are all 0, or actually any value, but now the leftmost 4 bits need to have a specific value. So which hexadecimal number has this value set? This would be, for example, if we translate that bit sequence into a hexadecimal number, that would be 10, 0x10. So anything starting with a 1 would be valid, I think. But also a 1 1 would be valid. Yeah, because if we have 1 1 here, then a 1 1 could be shifted right 3 times. Wait. Yes, no, shifted left 3 times and have the 0 flag set. I mean 2 times. This is 2 times. So we could pick here something that has, well, what can we pick here? This is 30 translated, because this is a hexadecimal 3 and this is a 0. So let's check out what this 30 is, and it's a record separator. This is not a nice character that the user can type. The characters that the user can type start here with the space and exclamation mark and quote, etc. So we can pick, for example, 1 1 1, because it doesn't matter which other bits are set. The important bit is this one right here. This one is important because this is what ends up as the 0 flag. The other bits can be whatever value is desired. And that's, by the way, why the author of that Crack Me writes that he wants to have a key generator, because a key generator can now generate inputs that have random bit values, but still keep the 0 flag that is shifted as some fixed value. So multiple keys will be valid here. This now is a 3/8, and it's the same thing as that. So this can be an 8 again. And let's copy that. And if we shift all of that by 1, then we get this, for example, this. I'm not sure if that is a good ASCII character. This would be a 1 1 1. That's a 5. No, is that a 5? It's a 7. So that would be 70. Which character is that? And again, multiple characters are valid here. 70 is a P. So we can use a P. But we could also use, for example, the 8 again. Because the 8 also contains this bit, which is set. And if it's shifted left once, then it's shifted into here, which sets the 0 flag eventually. But let's use a P just for fun. So this means our sample password is 2488p. Lowercase p is important, by the way. So this means our sample password is 2488p. All right, and let's go into here, or maybe into the, I don't know. No, here, this is fine. Let's go into here and let's try to call the flags with some password. And that tells us, I don't think that's the flag I was looking for. And let's try the password that we generated ourselves, that we found by pure assembly reverse engineering. 2488p. Thanks. That's perfect. And now, because we know that the password can be picked quite freely, and it's all due to these shift operations, and we just need a 1 at the 6th bit, counting from 0, of this byte right here, we can also find a different password, for example, one that stems from the fact that all the bits are ones. I mean, if we have all ones and they are shifted left, then the 0 flag will also be 1, because this is all ones. Then it will just append zeros to the right hand side, but this will, but the 0 flag will be 1, because all ones are shifted left. What would that 111 correspond to? 111 would be hexadecimal. This 111111111 would be hexadecimal 0x88 or 77. No. What am I talking? FF. This would be FF. And that would be an ASCII. ASCII. Let's check. I think there's nothing for it in ASCII. Great example, but maybe let's check one that is available. For example, 00111111. That would be a 3F. Let's check out 3F. In ASCII, it's the question mark. So let's try this one. Let's try it again with a wrong password. Wrong. And let's try it with our question marks exploit. And it says, thanks, that's perfect. And that's because the question mark ASCII character sets so many bytes such that when they are left shifted, they always keep the 0 flag 1. All right, so as you can see, multiple passwords are possible here, and that's why this guy is asking for a brute forcer. If you want to write a brute forcer, have fun writing one. Basically, you just need to keep 1 byte or 1 bit constant in the byte, and then set the other ones randomly according to or keeping attention to the shift operations, of course. And let's just try to generate one more valid password just for fun. For example, we can alternate, let's say the second character, the 4, can be replaced by, let's just set, this is the important bit that must be 1. But we can also set, for example, this bit right here 1. That would result in the value, This is a 4 and this is an 8, so the value 12, which is a hexadecimal C, I think. So we need anything with a C at the end. Any character with a C at the end, for example, a comma. Let's try the comma. So flags 2,88p, and it accepts that one as well. And guys, that's how. That's a big story. We just made something awesome. How can I create a view of everything that we've done today? cd crack me, and then our solution is down here. No. Less solve. Or maybe less solve. Like this. This is our solution. And then in the rightmost pane, we are we are calling it with our sample password 2,88p. Thanks. That's perfect. All right. And this is how we reverse engineered pure assembly code. I think it was a lot of fun. And if you enjoyed this and you want to see more such content, then stick around and put your feedback in the comments. I find that going through the pure assembly code and annotating it with my own comments helps a lot in understanding the assembly code, because the brain discards or keeps discarding all the information, and this just keeps everything fresh so that you don't have to reinterpret every instruction. You can just look up what you already found out. So that's very useful. All right. So if you enjoyed this, then leave a like and stick around, and see you next time. And for the rest of the day, spend your day positively, do something nice, and I will bite into this delicious sausage right here. Bye bye.